Good morning. My name is Sean Osterwise,
My name is Stephen Moseley.
And my name is Heather Pierce.
and we are students in ME3210 Design and Manufacturing Section B. In the next 15 minutes, we're going to be presenting on Project 4. Project 4 is a group research project where we have been given a list of 17 selected topics throughout the course. We have been asked to research all 17 topics and give a presentation on our top 10. These 10 topics will be presented by the three of us in no particular order. Let us begin.
Generative design is an advanced algorithm-driven process often utilizing AI to explore a wide variety of design possibilities that meet predefined criteria set by engineers or designers. This is a great way to use computing power to reduce used material as well as component weight, as the computer can determine where supports are needed and exclude any extra material. A good example of where generative design is used is architecture, to help engineers and designers create structures that optimize for aesthetics, sustainability, and performance. This allows for the general purpose and shape of the building to be designed to fit the skyline, and AI can generate the internal structures to make the design work. Another way is it is used in the creation of personalized medical devices such as prosthetics or implants to fit specific patients. Generative design has also been applied in the automotive field when designing strong and lightweight components. This method of design is not often used for parts going into mass production because the parts look alien, almost like stretched out slime. This means they will require serious machining work or advanced additive manufacturing techniques, which are neither fast nor cheap.
Plastics are synthetic or semi-synthetic materials that are used in many products, from milk jugs to medicine bottles to food containers and packaging. Since their creation, plastics have quickly become a major part of the modern world. Their inexpensive and easily moldable properties have made them an easy solution to creating new products for everyday use. The inexpensive nature of plastic has made them widely used for single-use purposes. This greatly benefits the medical industry, where plastics play a critical role in maintaining sterilization standards. This also contributes to significant environmental changes. The large volume of discarded plastic overwhelms recycling facilities, leaving much of it to accumulate in landfills or pollute natural environments. As the demand for plastic continues to rise, finding sustainable solutions to mitigate their environmental impact has become a global priority.
Value stream mapping is a lean manufacturing tool used to visualize the flow of materials and information in the production and distribution process. A VSM displays all critical processes, beginning with the first step in manufacturing and ending when the product reaches the customer. A basic VSM is a flowchart loop where the information flows counterclockwise from customer to supplier across the top, and material flows from supplier to customer across the bottom. Paired with the material information flows are the lead times for each process. Real VSMs are often a lot more complicated, containing several interacting or overlapping processes. Value stream mapping started in 1995 with the Toyota Motor Company, which used the operating model to identify 7 types of waste: transportation, inventory, motion, weighting, overprocessing, overproduction, and defects. You'll often hear of the 8th type of waste, waste of talent, thrown in there as well, which will come up in lean manufacturing concept of Moody. Waste of talent is difficult to identify in a VSM, whereas the other 7 translate well into a waste of time, money, and or resources.
A digital twin is a virtual representation of an object or system designed to reflect a physical object or process accurately. It spans the object's life cycle, is updated with real-time data, and uses simulation, machine learning, and reasoning to help make decisions. Digital twins collect data from sensors on the physical object and update the virtual model accordingly. Advanced analytics can simulate scenarios, predict failures, or optimize performance. For example, in manufacturing, digital twins can identify when a machine part is likely to fail, enabling predictive maintenance rather than reactive repairs. Another example is in healthcare. Patient-specific organs or systems can be modeled for better treatment planning, and in aerospace, digital twins of engines are made to track performance and ensure safety when flying.
A minimum viable product is the version of a product that carries just enough features to be used by early customers. In other words, it is the simplest version of a product that you need to build to sell it to market. The product should work in all of the expected ways. For example, if it is a phone, it should be able to power on and off, charge, and make phone calls. It should not, however, have a gardening hose attachment or other unnecessary parts or features. An MVP serves multiple purposes. First, it can be used to test a product hypothesis with minimal resources. A company shouldn't spend all this money or time on a product that they don't know will be useful or will sell well. If it works, they can always sell a better version of it later. Video game companies do this all the time. Second, releasing a product sooner means that people can start purchasing it sooner. Companies and investors can start making back some of the money they've spent on development, and the brand can start making a name for themselves. Lastly, an MVP functions as a base for other products to spin off of. Amazon is the most famous example of a base product being released. It was a digital bookstore before becoming a digital store of everything else that can be bought.
Collaborative robots, or cobots, are robots that are safe for people to work with and around. They use advanced sensors and programming to detect and adapt to human presence, meaning they cannot hurt or even pose a threat to humans working in proximity, and can even manipulate the same part in tandem with a human. They are also extremely user-friendly. Coding knowledge is often not needed, as cobots can be taught simply by moving them around with your hands. Because of how safe these are, they do not require cages or lockout procedures like autonomous robots that are hard-coded. They have many more advantages, a few being they're extremely adaptable to different work scenarios and being relatively cheap compared to other industrial robots. Cobots can take on many forms that you may have seen before. They can be used to complete a manufacturing task, such as moving parts, welding, or assembly, and they are used for other tasks such as vacuuming, waiting tables, or food delivery in dense cities.
Design for reliability is a systematic engineering process that ensures a product or system performs its intended function over its expected lifetime. Every machine, every system needs to be designed for reliability at every stage of its product lifecycle. Designing for reliability during the early stages of development ultimately lowers the cost of production since individual parts will be less likely to fail. Several methods are utilized to ensure a product functions reliably. Failure mode and effect analysis is used to consider every way individual parts could fail and creating ways to counteract these failures before they happen. Fault tree analysis is a second method. This is a graphical method for identifying potential causes of system failures. However, these methods rely heavily on the engineer's ability to foresee potential failures. Only failures considered sufficiently likely are addressed with fail-safe mechanisms, leaving the system vulnerable to unexpected issues. If an unanticipated failure occurs, the result could be catastrophic. This highlights both the importance of testing, continuous monitoring, and iterative design to address anticipated and unforeseen reliability changes.
Benchmarking is when a company uses another, more successful company's products, services, or processes as a standard or benchmark for measuring their own. Benchmarking helps businesses understand how they compare with others in the market, with the ultimate goal of improving their competitive position. There are two classifications of benchmarking: technical and competitive. Technical benchmarking measures the process or product from the perspective of a designer or expert in the field, where competitive does the same but from the perspective of a customer. If the company performs poorly in technical benchmarking, the effort put in by the company may be insufficient and should not enter the competitive market yet. This is interpreted as a failure on the designers or creators. If a company performs poorly in competitive benchmarking, it may mean that the effort that they've placed is misguided, which is often a failure on the research or the management. Depending on the context, it could also be interpreted as a failure on the marketing. Benchmarking can pretty much cover any area of development within a company, from their finances to their products to their energy consumption to their productivity. If another company has published data on it, it's fair game. Sometimes benchmarks are purely quantitative in nature. Key performance indicators are measurements of a company's performance, for example, return on investment or employee retention rates. Within these measurements, companies can set targets or goals and base them on benchmarks created by other companies in the market.
Ergonomics is the study of how to design to improve safety and efficiency between people and the things they use in order to minimize the errors that may occur. This applies to engineering, safety, and the workplace. If you think of a simple office chair, there's padding for comfort, adjustability at height and angle, and armrests. Ergonomics and human factors provide comfort to the user in facilitating proper posture and reducing fatigue. This increases worker productivity and allows greater accuracy for the task at hand. Ergonomics can become costly, however. New equipment may need to be purchased and updated. Comfort and discomfort can also be incredibly subjective and vary greatly between different people. Adjustability in equipment can help to counteract this, but only to a certain extent.
The Kano model was developed in the 1980s. It is a tool that helps product teams prioritize features and understand how customers will react to them. Using questionnaires, product features can be categorized based on satisfaction and functionality, ultimately deciding what should be included in a product on its basic function and what the customer wants. When utilized correctly, the Kano model can help understand customers' needs and increase customer satisfaction by focusing on features that delight customers and ensure the basics are met. It can also use resources efficiently, as the model helps product teams avoid wasting resources on features that add little value to the product, directing focus on features that truly matter to the customers. And it helps gain a competitive advantage in the market by giving product designers an insight to what the customers actually desire, instead of assuming features that they might want. The main categories that features are broken down into are must-haves, delighters, basic features, and performance features, each category having a different level of importance to the function and human factors of the final product. Ultimately, by integrating the Kano model into a product development and management process, companies can better meet customer needs and expectations while simultaneously creating a product that is both functional and delightful.
The selected topics presented in Project 4, as well as the 7 that we have not discussed, all have something in common: their intent. Each selected topic was created to minimize waste and maximize efficiency in the design and manufacturing process. Generative design takes computing time instead of a designer's time, saving talent and weighting wastes. A digital twin reduces waste created by defects which could otherwise be found through physical testing. In doing so, digital twins also reduce inventory and other wastes associated with making physical prototypes. Plastics are inexpensive and relatively easy to manufacture and thus reduce the waste of overprocessing components. One could argue that their mass producibility could also reduce the waste of waiting times between processes. Value stream maps, several technical areas of benchmarking, and ergonomics are all designed to identify and minimize manufacturing process waste like transportation, inventory, and motion. Where designed for reliability, competitive benchmarking, and the Kano model reduce the market process waste of overproduction. Lastly, MVPs save time and resources spent on talent and overprocessing wastes, and the limited components or features limits the possible waste by defects. Ultimately, by strategically selecting and applying these methods, we not only enhance efficiency but also contribute to a more sustainable and cost-effective manufacturing ecosystem. Best, ME3210 Section B.